So if you recall, what we covered last class were the completion stage methods. I talked about completion stage methods where there's a single stage that triggers the next stage. So those would be things like then apply or then compose. We talked about the methods that are completion stage methods that will trigger when two previous stages complete, such as then combine. And then we also talked about completion stage methods that trigger when either of the previous methods, previous futures complete, previous stages complete. So those are the things that we covered last time, and you'll definitely need to know how to use those for the current assignment. What we're going to do now is we're going to show how to apply these completion stage methods to the big fractions example, and then we'll also show how to handle runtime exceptions. So it'll give you a little bit more exposure to the broader range of capabilities that are part of the completable futures framework. So let's talk about how to apply the completable future completion stage methods to a more comprehensive example. So you can go to my website at the EX8 folder and find a big test program that tests a whole bunch of things with completable futures. There's a particular method there called test fraction multiplications 1, which implies there's more than one way to do this, and there's actually a couple different ways of doing it. And as you can see, we've got a little stream here that does some cool stuff. So what this is going to do is it's going to generate a stream of bounded, it's going to generate a bounded number of large and random big fractions. So make big fraction is a factor method. I'll show you that in a second. That takes a random number generator, and false, which says don't reduce it, just generate non-reduced big fractions. And it only does this many of them. Let's say, for sake of argument, that that's 100, but it could be whatever. Here's make big fraction. As you can see, make big fraction is a factor method that creates a large and random fraction, or big fraction. And it does this by making a numerator, which is a big integer that's a random number uniformly distributed over the range from 0 to 2 to the 150,000th minus 1. So that's a pretty daggone big fraction, right? And then it goes ahead and makes a denominator, which takes the numerator and divides it by a random number between 1 and 10. We then go ahead and use the value of factor method to create a big fraction that has that very large numerator and that smaller denominator and a flag that says whether to reduce it or not. In this case, we're not reducing it. This is obviously a method that's going to take a while to run because it's a pretty huge big fraction. We're then going to take that stream of big fractions and we're going to reduce and multiply them. And as you'll see in a second, that's all going to take place in parallel, which is pretty darn cool. And we're going to use the map method. So what map is going to return here will be a stream of completable futures to these reduce and multiplication operations that are all running in parallel. Here is the reduce and multiply fraction function. So as you can see, what this thing does is it takes an unreduced big fraction, and it's basically a lambda, and it's going to go ahead and asynchronously reduce and multiply the big fraction, the unreduced fraction. It does this by asynchronously reducing the big fraction, so it's going to take the unreduced fraction and reduce it asynchronously. So we're using our good friend supply async, which is this factory method that starts the wheels in motion. Remember this when you do your programming assignment, because one of the things you'll do is one of these things. And then we take the results of this, and then we go ahead and asynchronously take the reduced fraction and multiply it by some big fraction constant. And in this case, we use then compose in a flat map-like way to ensure there's only one level of completable future nesting. So if we tried to use, say, then apply, we'd end up with a completable future to a completable future, which we don't want. So instead, we can use then compose, which takes this asynchronous operation and strips out the nesting so there's only one level of completable future. So that would be one way to do it. Here's another way to do it, which I actually like better. Another way to do this is to use then apply async instead of using then compose and supply async. We can just use then apply async, and we give it the reduced fraction, and we multiply the reduced fraction by the big fraction. And that doesn't require require us to call supply async again with then compose. So then apply async does what we want in a more concise and parsimonious way. Okay, so that's what that lambda variable does. So again, thinking about what happened here in the line that's not highlighted, map, reduce, and multiply fraction takes a stream of random big fractions that are unreduced and reduces and multiplies them in parallel. How do we know it's in parallel? Because we do these things asynchronously. There's a lot of asynchronous operations that are taking place here. So what comes out of map will be a stream of completable futures to these reductions and multiplications that are taking place in parallel. So let's assume, for sake of argument, we've got 100 of these operations that are all running. As you can see, they may take a while to run because these are pretty gigantic fractions, and we're multiplying them and reducing them, and that is going to take a while. So what we're going to do here is we're going to use a really cool future collector, or futures collector, which is going to take a stream of completable futures as input, and it's going to return a single completable future that will complete, that will trigger when all of the other completable futures are done. So this is basically going to allow us to do sort of a reactive mechanism to be notified when everything else is finished. So we basically are reducing all these completable futures into a single completable future. And we'll see this futures collector to future thing that we use to do all this. And then we will have this method get called back, the one called then except, when the one and only completable future completes, which only completes when all the completable futures it was waiting for complete. So this is something called an arbitrary arity method, and we'll cover that in more detail in just a second. So when then except gets called back, at that point, at long last, we're going to end up with essentially a list of all the completable futures, or all the computations that have just finished running asynchronously, and we're going to go ahead and sort and print that list. So when everything is finished, we're going to go ahead and sort and print the results. Here is sort and print list. This is going to sort and print a list of reduced fractions, and it's going to do it in a ridiculously clever way, leveraging the fact that we have way too much parallel cores these days, so why not take advantage of them? What we're going to do is we're going to go ahead and asynchronously apply quicksort and asynchronously apply merge sort to the same list. So we're going to sort the list of reduced and multiplied big fractions now that they're all finished. We're going to go ahead and quicksort them and merge sort them in parallel. And then we're going to take whichever one finishes first, and we're going to go ahead and print the results. Yes? So if you had more than two, so the question was, can you chain these things together if you have more than two? So except either, of course, just works with two. If you have more than two, what we would probably want to use is the arbitrary arity method, like any of. There's a method called any of, which takes n completable futures, and it'll come back with whichever one finishes first. So we could do that, and you'll see how that would work. In this particular case, we're just using two, but you're right. If we wanted more than two, we could use any of. You'll see how I use all of in a second. You could have a similar thing of doing for any of, which would be very cool. So this one's going to go ahead and select whichever result finishes first. If quicksort finishes first, we'll take that. If merge sort finishes first, we'll take that. And in either case, whichever one finishes first, we'll take the sorted list that comes back, and for every element in that sorted list, we will display it as a mixed string. So the way this works is that if the future has already completed, if these things run and they finish so fast that one of these futures is done before this even gets called, then the calling thread will be the one to run this for each method. If they're still running when this gets called, whichever thread the previous stage completes in will be the one to run this computation. Remember that except either doesn't cancel the second future after the first one completes. It's still out there doing its thing, even though in this particular case we're going to ignore the results. But it doesn't cancel it. OK, so that's a nice little overview. And this will give you also a few more tips for how to do your assignment number 4, although assignment number 4 is much more involved than this. Let's talk about exceptions. So when you write a regular Java program and something goes wrong, then you typically have a try-catch block, or you could have the potential of a try-catch block, and your try-catch block would be there to receive the exception that was thrown. You could catch it. You could have some kind of exception handler. That's a way of handling exceptions in a synchronous manner. That, of course, raises the question, how do we handle exceptions in an asynchronous program using completable futures? And the answer is you use one of the various exception methods to do this. It turns out that there are actually 5 exception-oriented methods in Java completable futures. 2 of them have variants. So when complete has a when complete async, and handle has a handle async. And one of them, exceptionally, only has one implementation. And I'll talk about all these things in a second. This just gives you the top level view, and I'll show you examples of them all. So I'm going to use the following simple example that actually is demonstrated here in the EX folder in my GitHub repository to show these different ways of handling exceptions with completable futures. So let's assume, for sake of argument, that we've got a piece of code that's going to asynchronously create ourselves a big fraction that has a numerator of 100 and some denominator that's a variable. And if you look at the test program, you'll see that sometimes denominator is non-zero, sometimes denominator is 0. So, of course, if denominator is 0, an exception is going to be thrown, because we're going to end up trying to create a big fraction that has a denominator of 0, which will, of course, be a bad thing, because you can't divide by 0 in any sensible way. So the first way we're going to do this is we're going to show how to use the handle exception method to handle either exceptional or normal completions. So let's assume that we've called supply async and say that it was a non-zero denominator. In either case, the handle method will be called, and this will be used to handle the outcome of the previous stage. So if, for some reason, fraction equaled null, that's an indication that an exception was thrown, because the value is null. There was no actual big fraction value that came back from this. So in that particular case, that's the exception path, and we're just going to return big fraction 0. So if you try to divide by 0, we're just going to return a 0, which is kind of lame, but I'm just trying to show the example. I could also have checked to see if EX was not equal to null. That would have also indicated whether something went wrong. If we don't get an exception, then we can do the normal path, which is just to multiply the fraction we created here by some constant and return that value. OK, so that's kind of how handle works. Handle must return a value. Every branch in the handle method, in the lambda expression portion of this, must return a value. And therefore, you can change the value. You could, I mean, it wouldn't make any sense here. You could also just return fraction, but we're trying to do something to it. So you notice we have 2 branches, and we have to return values in both places, and therefore handle can have the side effect of changing the result. Here's how to do the same sort of thing using the exceptionally method. So in this case, once again, let's assume we have a denominator that's 0. Then what will happen is the then apply method here in this fluent chain is going to be skipped. So when an exception is thrown, it gets propagated through the chain of completion stage methods until it finds one that knows how to handle the exception, which in this case is exceptionally. And you can see that exceptionally is going to do something. It's going to convert the exception to a 0 result. Again, maybe not the best thing to do, but just to illustrate that we can take an exception and do something and then transform the result. And that's what comes back as the result of this stage in our fluent chain of completion stage methods. So you can basically think of exceptionally as kind of like a catch in a Java try-catch block. In other words, control transfers from where the exception was thrown to the place where the exceptionally is defined in the fluent completion stage chain. Let's then take a look at the when complete method. And the when complete is a little bit different from the other 2 examples. The other 2 examples really handled the exception in some interesting way and then changed stuff, changed results. When complete is a little different. It will always be called. So whether there's an exception or not, when complete will always be called. However, based on the parameters that are passed to it, the behavior can vary. So in this particular case, if fraction is not equal to null, that means things worked. We actually were able to create a valid big fraction and multiply it and reduce it and so on. And if everything went according to plan and there were no zeros and so on, then we're going to go ahead and print the fraction as a mixed string. However, if fraction was equal to null, in other words, EX was non-null, then in this case, we're going to print out the exception error message that says, divide by 0, or whatever the exception message would be in that particular case. Now, when complete's a little different because it doesn't change the result. The result is still whatever the result is. It just has a side effect, which in this case is printing something. And so in some sense, it's a little bit like the Java 8 streams peek method, where peek is a method that can be used to give you some information about what's going on in a stream without changing anything. It's just a way of, it's usually used for logging or debugging or something like that. So when complete's a little bit different from the other two methods. It can't change the result. Okay, so that was a quick overview of using Java 8 completable futures for some simple program that does multiplication and reduction of big fractions, and then also taking that same suite of examples and showing how exceptions can be used to process the results in a sensible way.